gave my first lecture, and what I talked about was this regime here at very low Reynolds number, and what I showed you in great detail was that small does not mean negligible. That very small Reynolds number does not mean Reynolds number equals to 0, and we saw how complicated it is to compute in particular drag and other things in this regime. What we're going to talk about today is very high Reynolds number flows, and the reason why my lectures are here and here is because I was asked to talk about the connections between statistical physics and condensed matter physics and fluid mechanics, and often those connections invoke some kind of universal behavior, some kind of universality. So the lesson is that universality usually occurs when something is very small or something is very large. And usually in between, where things are of order 1 or maybe of order even 1,000, that's still small, something very complicated happens, and it's very difficult to say what happens. There's nothing universal, there's nothing simple that one can say. Nevertheless, there is stuff that can be said around here, and it's very important to study and so on. And Bruno Eckhard will be talking about transitions to turbulence later on today. All right, now I'm going to start off today by asking a very simple question: how fast does a river flow? And there's an experiment that you guys can do as an exercise, in addition to the ones I gave you last week, which is you can go to Canyon, to the Canyon street where there is a river flowing through it, very high. You can actually go and take measurements and try to calculate and observe how fast the river flows there. So we're going to talk about how fast rivers flow, then we're going to talk about something called Richardson diffusion and structure functions, and then I'm going to explain to you in detail the energy cascade that Dan Latham talked about in his talk, and derive for you some of the formulae that he showed there, and I'll show you how one constructs scaling laws and understands what is known as the inertial law. And also, in the scope of this lecture, I'm going to be able to cover some of the exact results that are known about turbulence. So luckily, virtually nothing is known about turbulence, and very little is known exactly, so this will be a very brief section. And then at the end, I'm going to talk about turbulence in 2 dimensions, because I want to give you some background about that so that you'll understand the second lecture that I'm going to give tomorrow. So let's start off then with a very simple question. How fast is there a question already? Okay. How fast does a river flow? And this is a good question. Many people have asked this question, but Kolmogorov, who was one of the great stars of turbulence research and perhaps the greatest mathematician of the 20th century, was interested in this question himself and realized that there was a really interesting issue here. So let's set this problem up. So we're going to imagine that we have a river that flows down from some mountains down towards the sea. It does that over a distance scale that we'll call L. It has a height between the entrance and the exit is we'll call H, and then the river has some depth, which we will call D. So there's the river. This scale we'll call D. Gravity is pointing down, and the slope here we'll call theta. So what you would naively do is you'd say, well, we know about the Navier-Stokes equations because we've learned about them all last week. So you know that in steady state, you're going to balance the gravitational force with the viscous force. So you're going to have a term that looks something like this. There's going to be a new d2u by dz squared, and that's going to be balanced by g sine theta. And so we can now integrate that equation up and work out the flow velocity inside the river here, work out the velocity profile as a function of the depth, and then work out the mean velocity that the river is flowing in this direction, we'll call that u bar. And what you will get, if you do that, is g sine theta d squared over nu. And if you put in the parameters for the river Volga, So you put in, so D is about 10 meters, L is about 3,000 kilometers, H is about 300 meters, theta is about 10 to the minus 4. Then what you get is the speed at U bar is about 10 to the 7 centimeters per second. Okay, that's really moving it. So our idea that laminar flow, everything that we did last week, describes anything in the real world, something as prosaic as overflowing, that's clearly very far from the truth. As Dan said in his talk, essentially the genetic state of fluids around us is that they're turbulent. Well, then you say, of course, this is a stupid idea, because what we should have done, we should have said, well, look, the fluid has some potential energy up here. By the time we get to the bottom, it has some kinetic energy. So what we should be doing is looking at the energy balance. So let's try again. So second attempt. So what we're going to do is ask what speed you get by converting potential energy to kinetic energy. So that's the question, and so that's easy to work out. What we have to do is basically balance a half rho squared versus a rho gh. In this case, we get that u is the square root 2gh. We work that out, and we get that u is about 10 to the 4 centimeters per second. So it's still a much smaller fraction of the speed of light than our previous estimate. That's still a little fast. So what's going on here? So what's going wrong is that we're neglecting the fact that we are dealing with a nonlinear equation. So we wrote down the Navier-Stokes equations last week, and you know that there is the term u dot grad u, a nonlinearity in the equations, and we just ignored that last week because we estimated that this thing relative to the viscous dissipation is of order the Reynolds number and can be taken to be small. But when the fluid is flowing very rapidly, then this term becomes more important. So this term becomes important as the Reynolds number goes up, and in fact our previous estimates don't make any sense for large Reynolds numbers. Now this term, is, as we saw, comes from inertia, and so what that means is that as the fluid starts moving faster and faster, it's driven more by the inertia, by just wanting to go in the same direction, and the viscous dissipation part becomes relatively negligible. So I'm now going to show you how to estimate the speed of a river. I'm going to do it with an argument that at first won't make very much sense. It'll seem kind of odd, but we'll get the right answer, a roughly right answer. And then later on in the lecture, you'll see more precisely where that kind of argument comes from when I get to show you about the speed of rivers. So what we're really going to be saying is that our picture of the flow is that you have a bunch of turbulent edges like this, okay? Now Leonardo da Vinci can draw them better than I can, but basically that's how he draws them, that's how anybody draws them. So these are some kind of edges, and they're not very well defined. If you ask a condensed matter physicist to talk about their subject, they'll often use terms like quasi-particle, okay? And you might say, well, what actually is a quasi-particle? I mean, in a solid, in a metal, the quasi-particle is really just a fancy name for an electron that doesn't seem to experience Coulomb forces, right? So quasi-particle is a kind of funny concept, but it has a completely precise mathematical definition in terms of correlation functions and quantum field theory. In turbulence and fluid mechanics, we don't really have a very clear picture of what an eddy is. It's some kind of dynamical degree of freedom, some kind of motion of the fluid, some kind of collective motion of the fluid, look something like that, and you know it when you see it. So what we're going to ask is, well, if we have a river in some depth, d like this, We want to ask how are the eddies flowing around in that river. So what you might say is, well, let's ask how long it takes typically these eddies to circulate. So you might say, well, there's a thing called an eddy turnover time, which we'll call tau, and we'll define it in more detail later on. That's going to be basically, in terms of dimension, it's going to be a length scale over velocity, so we'll write it as d over u. We can ask what is the energy of each of these eddies. So we could estimate that by saying the energy is going to be something like the cross-sectional area of the river. So there's a cross-sectional area, which we'll call A, out in this direction. So there's a cross-sectional area times the depth times the density times u squared over 2. And we can ask how much energy gets dissipated in an eddy as it rotates and spins off other eddies. So we could say the energy dissipation rate So how can we make a dissipation rate out of this? Well, we have an energy and we have a time, so that has to go something like E over tau, and so that has to be something like A, L, rho, can I write this over here in a different colour so you can see it? A, L, rho, u squared over 2 times u over L, and that's going to be rho A over 2 times u cubed. That's a very strange functional dependence, a u cubed dependence. Right? Now, this dissipation is due to gravitational friction. So, what we're going to do is equate that to the work done against gravity. So, dissipation is going to balance the work done against gravity. So that's going to be the rate of working is equal to the force times the velocity. So we can estimate that as basically W goes like rho AG L sine theta times the velocity times U. And if I equate epsilon and W, what I then get is that rho A over 2 u cubed is rho A G L sine theta times U. Or in other words, one of the factors of U cancels, and so I get U goes like the square root of 2GL sine theta, and that gives you a number that's about 10 centimeters per second. Isn't that a curious argument? It's a very curious argument because I never included viscosity. We never had to worry about that. All we cared about was the inertia of the fluid. It's just swirling around and doing stuff. So this is a very interesting kind of idea, because this is a dissipation and a state of motion that, as Dan said, is emergent. It didn't depend upon the underlying parameters of the fluid. It didn't depend upon the viscosity. It didn't depend upon anything really. It just depended upon the actual state itself. So let's write that down. So this is strange. It's strange because it does not depend on viscosity. It's governed by the inertial motion fluid, and so it's some kind of emergent property of being turbulent. Now, emergence is, of course, a very big concept in condensed matter physics, and what does it really mean? It means that it's something that comes out collectively from the motion. So let's suppose that you sat there and you decide, I'm going to solve turbulence. The way I'm going to do it is I'm going to solve the Schrödinger equation for all the fluid particles. I'm going to go and derive everything and so on. You might have to some huge amount of supercomputer effort be able to work out the viscosity or whatever of the fluid, but you never have been able to come up with this because this didn't require any of those things. So the nature of the turbulent state somehow got disconnected from all the fundamental fluid properties below. So that's the idea that we're going to talk about today. Okay, John, you have a question?
Yes. So when we made this dissipation balance over here, did we
Yeah.
make some thermodynamic assumption?
No, we just made some crude sort of back pocket idea that we just look at the way it's working, we balance that with the dissipation, and what we're assuming, and most importantly, is we're assuming that we're in some kind of non-equilibrium steady state. Okay, so that everything gets balanced, so that nothing is in the end changing with time. So all my average quantities of the flow are going to be constant, so everything balances. Of course, that's a gross simplification, but that's the kind of thing that we've done. So, yeah.
Can you comment that, but for this estimate to be sense and not nonsense, you do have to assume that there is a thermal dump for the energy.
Absolutely.
So you
absolutely.
are assuming that energy is going to heat in the liquid.
Well, we're going to come to it.
So there's a thermodynamic aspect to this argument. That there's a heat sink.
There is, but it gets curious because there's a thing called the dissipation anomaly, which I'm going to talk about in a little bit. So, but yeah, so but ultimately, when you get down to a very small scale, you get down to microns, molecular viscosity is going to become important. And that ultimately is when I talk about the eddy dissipation ratio, what I'm going to explain to you in a few minutes is how the energy is flowing down from scale to scale to scale, so eventually it gets down to a scale at which this estimate ceases to be valid. I'm going to exactly work out for you what that scale is and derive a formula that showed in this history. Someone has a quick question?
I have another question.
Yes.
Sorry, I don't want to be picky, but
Yes.
this velocity that you were mentioning, I mean, we know that the side of the rivers, they're flowing
Yes.
more slowly, and then
That's
the center.
correct. That's correct. So this is an average velocity.
Okay.
So imagine that you take a velocity profile. That means you take the velocity as a function of distance from the bottom, as a function of distance from the sides. You get some shape. Velocity is a function of x and y,
Yeah.
and then you get the average. So this argument is just meant to be a dimensional argument, just to give you some feedback. And I'll talk a little bit about the velocity, about it being slow at the walls and fast in the middle at the end of the lecture if I get time. Okay, another question, yes.
Yeah, I had a question about the scaling that you for the time.
Yes.
You took the length scale to be d, the depth of the river,
Yes.
right?
Yes.
But the rest of everything, it seems to be solely dependent on that.
Right, I needed that to estimate my eddy turnover time. But you're right, it doesn't really make much difference. That's fine. And we're going to go through this in a bit more detail later on. Okay, so what is odd about this is, so another one thing about this that I want to mention, so as a separate point.
I have one last question, maybe.
Okay, so this argument is meant to be provocative, okay? I'm not answering these questions during the rest of the lecture, okay? So go ahead.
How do we know that that's the right answer? Because, I mean...
I'm going to explain that at the end of the lecture, you'll know.
Okay.
Okay? Okay? So yeah, you're perfectly right. It seems very strange, okay? So that's why I'm saying it's strange. It's an unfamiliar, weird kind of answer. So here's another thing that's strange about this. So usually you're used to thinking about the force as being proportional to the velocity. That's what we did all of last week. But here, I've got an estimate that the dissipation rate, epsilon, is going as u cubed. That's this unlikely formula that I ended up with, u cubed. Okay, that's strange. So that says this is laminar. And here, I've got epsilon going as u cubed. So that suggests that the frictional force is going as the derivative of this, is going as u squared. So what happens is when you have a turbulent drag, it's not just proportional to the speed, it's proportional to a higher power of the speed. That's why if you could understand how to reduce drag in aeroplanes and automobiles, you'd save billions of dollars in fuel every year. Okay, so that's the sort of introduction to the key weirdnesses of turbulence. Now this formula here, this goes back to Mr. Chazy in Paris in the 1700s. He was trying to devise ways to make aqueducts and canals and sewage systems in Paris in the 1700s. And so he already realized that if you want to work out how much flow goes through a river, it has to go as u squared, and therefore he could have also made this deduction here. This formula is generally thought of as being something that comes from Kolmogorov. Okay, so that's the idea of drag and what's strange about turbulence. In my notes, I have a whole extra section on what in detail the drag looks like as an object moves at ever increasing speed through a fluid. And in fact, I also have some comments about how golf balls are designed, why golf balls have little dimples on them, and there's some comments about boundary layer separation. So you can read those if you're interested. So the next thing I want to do is I want to move on and talk about turbulent diffusion and Richardson. So let me clear the board here and get to the next level of detail. So Dan already talked about how turbulence is important, for example, in an automobile engine, because it governs the rate at which things are transported in the flow. So I want to now discuss exactly how that happens. So this is, I'm going to call this turbulent diffusion. I believe later on in the week you'll get some lectures on passive scalar advection. So this is a sort of introduction to that. So let's suppose we have a laminar fluid. Then what's going to happen is that heat, for example, is transported by just regular diffusion. So heat transport by diffusion. If the fluid is turbulent, for example, by heating it from below, so you get convection, and the fluid itself is moving, and as the fluid itself moves, it can transport heat or anything else with it, and you might think you can do that in a much faster way than it would be able to do if the fluid was just laminar. So in turbulence, what you expect then is that transport is enhanced by the convective motion of the fluid. So let's do a simple calculation that shows something like that. So what we're going to do now is a simple calculation that says the following. I'm going to take two points in the fluid. We have a separation R1 minus R2. We have a velocity field, velocity R1, velocity R2. And we're going to ask, how does the separation between them vary as they flow in the turbulent fluid? So what we're actually going to be interested in is the distance between these particles. So what you would expect is that the distance would go something like some diffusion coefficient times t all to the power half, or you might therefore say that d by dt of r squared should be a constant. Okay, so that's what you would normally expect. Okay, but that's not what happens. So let's see what actually does happen. So we're going to see what happens by making a very crude model, an idealization of what a turbulent system looks like. We're going to assume that the turbulent fluid is a kind of random velocity fluid. So what we're going to assume now is a simple model. suppose is that if I look at the time difference, the derivative of the change in the velocity between these two particles, I'm going to assume that that is basically a random force. There's some random force that's acting on the particles and driving them apart. And that random force then we'll call delta F, which is some random function like that. So what I've written down for you is a stochastic differential equation. And what I'm going to assume is that F is basically just a Gaussian distributed variable. So if I compute delta F at t, delta F at t prime, look at its correlation function, that's going to be something that is basically given by some constant times the delta function of t minus t prime. So it's just some kind of white noise driving force. So then if I were to then calculate what is the correlation function of the velocity at time 1, the velocity at time 2, what I have to do is I have to integrate up that, I have to integrate this equation. I've got d by dt of delta v is delta f of t, so now I have to integrate this up, so then I get the integral of delta f is equal to delta v. Now I have two of them here, so I have two integrals. The integral from 0 to t2, the integral from 0 to t1, delta f of t1, delta f of t2, dt1, dt prime, and that's how I can compute the velocity correlation function. So now you have to do this integral, and so what happens is you have to replace this by delta of t minus t prime times 6 epsilon. And so that's an exercise for you to do that integral. You have to be very careful about the limits. You have to be careful about whether t1 is greater than t2 or less than t2. But if you do that, it's a few lines of algebra to get 6 epsilon times the minimum value of t1 or t2. So whatever is the minimum of those, that's what this integral is equal to. Okay, so now I can say, well, let me set t1 equal to t2. And that then tells me that when I compute delta v t squared, that's going to go like 6 epsilon times t. So far, so good. So now I want to ask, well, how does the deviation between 2 points go? So what I ask then instead is how the difference between 2 points goes as a function of time. So I'm going to integrate delta r squared. And now for that, I have to take, since the distance is the integral with respect to time of the velocity, so this now is going to be just the integral from 0 to time, the integral from 0 to time of delta v t1, delta v t2, dt1, dt2. I have to put this formula in there, and again, that's just a couple of lines of algebra. So that's another exercise for you to complete. And what you'll get is you'll get the 2 epsilon times t cubed. So what we've learned then from this simple argument is that if you work out what that means for d by dt of r squared, what that translates into is not that it is equal to a constant, that d by dt of r squared is equal to a constant. What it actually says is that d by dt of r squared goes like r to the 4/3 power. And that's known as Richardson's law. Another way of saying it is that dr by dt goes as r to 1/3. But this is kind of strange. This is not the usual type of scaling that you would expect from simple diffusion. And the reason it isn't is because what's happening here is we're mixing up random processes with kinematics. What we're doing is we're writing down dynamical equations for kinematic variables like velocity differences. That's because we're looking at inertially driven flows. Okay, so let's look at another corollary of this.
Question. Is it fair to say that the velocity is diffusing in this case?
Yeah, no, I wouldn't say it like that. Okay, so let's suppose I now ask the following. Let's suppose I ask how far something has gone. So that's x dot is just given by v of t and x. So that's how I define the velocity of a fluid packet at any given time. So that then says that if I look at the velocity at x1 in time t minus the velocity at x2 in time t, and that's going as x1 minus x2 to the 1/3. Now what we're going to be concerned with in turbulence is not just looking at tracer diffusion. We're going to be interested in looking at the correlation functions of the fluctuating velocity fields at any given point. And typically the way we look at that is we look at quantities which look like this. So we look at usually longitudinal velocity differences, which I'll write in this way. UR is defined to be U of x plus R, and U of x, dotted with the vector that goes between those 2 points, something like that. So that's how I'm going to define a longitudinal velocity difference. And the idea of this is to look at the component of the velocity along the line connecting 2 different points. That's what we want to do. So what we're going to end up doing is, later on, we're going to look at, when people like Dan measure, the structure functions. And these structure functions are usually defined in the following way, up to coefficients. We're going to define the nth order structure function to be the expectation value of VR raised to the nth power. So we're going to be interested in the probability distribution of velocity fluctuations in our turbulent field. So what does this thing tell us? So this thing tells us that V, the delta V, goes as x to the 1/3. So that might suggest to you that if I were to look at the 3rd order structure function, just multiplying this to the cube power, this thing cubed would go as x. So that would suggest that S3, the 3rd order structure function, would be something that scales with the separation R. And in fact, we're going to see that this is indeed true. This is one of the famous rigorous results, the exact result that we can get in turbulence. Okay, so that's a kind of introduction to the strange, counterintuitive kinematics of turbulence. Is there a question? Do you have a question?
Yeah, index, and what does the 3 mean? I'm sorry, that's the 3rd.
What is V? I think I meant U. Sorry, U. I'm sorry, I switched between velocity being U and velocity being V. Sorry about that. That's kind of gauge symmetry of physics.
Excuse me, you did a force correlation.
Yes.
Why did you have the 6 epsilon? Because
I can choose any normalization I like. If you follow this through in detail, this epsilon is going to turn out to be the energy dissipation rate that we talked about before, and I'll talk about in a few minutes. So that's just another way to derive it. So what I want to do now is I want to talk about the cascade concept, which I would argue is the most fundamental aspect of turbulence. So lots of problems in physics have stochastic variables that fluctuate, but only turbulent ones have a cascade, and so I want to explain to you what a cascade is.
So before you do that,
What was the question?
yeah. So I mean, so the field, the velocity field is clearly non-Gaussian. I mean,
Yes.
So then why are they?
Well, the velocity field, well, if you measure that, you have to distinguish between velocity and velocity gradients. So velocity gradients are not Gaussian. Velocity itself is Gaussian, right? From down to gradient.
So these are velocity gradients.
In a sense, because we're looking at delta.
So you're not suggesting that it's as simple as everything reduces to the first moment. It's just this.
Absolutely not. Absolutely not.
It's
By
just
no
the
means.
third number.
Yeah, absolutely not. We're going to talk about all of these things. So let me just say then that the fundamental aspect of turbulence is the presence of a cascade. Now I work on turbulence and I write proposals and often, although as you'll see next lecture, I will tell you about some work that we've done on three-dimensional turbulence, but also how we tested the theory by looking at what happens in two dimensions using turbulent soap forms, and I'll show you all of that tomorrow. Now, one of the interesting things is that nobody at the National Science Foundation knows how to review these proposals, because they look partly like engineering and partly like condensed matter physics. So what happens is that the proposals are usually well reviewed, except there's usually an engineer who is there who will write down a review, which would be typically a one-line review, which says you can't have turbulence in two dimensions. It doesn't exist. And the reason that they think that, as I'll show you, is because you can't have a vortex structure. So actually what turbulence actually is a real question. And I think that the important point to bear in mind is that you have a cascade phenomenon, and that's the fundamental aspect of it. So it's not just something special that happens in three dimensions. You have to be able to think forward. So so in my notes, which I'm going to spend time here going through, I'll just read to you a little bit on what Leonardo da Vinci wrote. So Leonardo was very famous, drew a very famous picture of turbulence, and it's a nice one. And he said, observe the motion of the surface of water, which resembles that of hair. It has two motions, of which one is caused by the weight of the hair, the other by the direction of the curls. The water has eddying motions, one part of which is due to the principal current, the other to the random and reverse motion. So you have the idea that you have a net flow, which is the river just flowing downstream, but then superimposed on top of that is the random, chaotic in quotation marks, not technically chaotic, motion of the fluid. And the small eddies are almost numberless, and the large things are rotated only by large eddies and not by small ones, and small things are turned by both small eddies and large eddies. So Leonardo already had the idea that you have large motions that are kind of slow, and then small motions, and then smaller motions still, which are smaller and smaller and smaller. So that was the idea, that's the pictorial idea of a cascade, and Richardson, who in fact developed this scaling law back in the 1920s, had a little poem about that. So I'll tell you his poem. So this poem goes like this, and even way up. It says, big worlds, the middle worlds. The world is an eddy, which feeds on their velocity. Little worlds of lesser worlds, and so on to viscosity. Okay, that's Richardson in about 1926 or so. And so that's a picture of a cascade process. So up here, at this scale, energy is input, as you stirring it with a propeller, with your fingers or something like this. And then down here, eventually you get to a small scale where things start rubbing against each other and you get virtual heating. And so that's the effects of viscosity. So this is the idea of what the cascade is. And later on in the when I get to talking about turbulence in two dimensions, I will ask you as an exercise to compose a similar poem to this, to take your mind from the mathematical exercises I've given you in the last few days, to explain what happens in two dimensions. Does anybody know what poem this is a parody of? Anybody ever seen this before?
The little bugs that bite them.
Sorry?
I don't remember the title, but the
Yes.
little bugs that bite them.
That's right. Again, it's a parody of a poem, which itself is a parody. So this is a parody of a poem by Jonathan Swift. It was written by August Morgan, and it says, big fleas have little fleas upon their backs to bite them, and little fleas have lesser fleas, and so on, ad infinitum. And then there's a second verse to that which goes, and the great fleas themselves in turn have greater fleas to go on, while these again have greater still, and so on. Okay? So that's a kind of poetic 17th century version of scaling theory. Something that is scaling theory. So what I get from these whimsical pictures is that we expect some kind of scaling variance. And indeed, that's what I'm going to experience in a moment. So the basic idea then is you have a cascade. You might ask, of what? In fact, we're going to see that that question is a non-trivial question. And we're going to see that there's a notion of scale invariance. Now, here, I'm going to now tell you the fundamental insight that Kolmogorov had that is truly fantastic. Okay? So the insight is you might look at this. You might look at these eddies going down small scales, and you might think to yourself, aha, that is just the system breaking up and slowing down and grinding to a halt. Well, that's not true. What Kolmogorov realized was that this process is a Hamiltonian process. Okay? Think about that. That's completely non-intuitive. That is Hamiltonian. That's sort of all the idea that the viscosity is slowing these things down and making them fall apart. That's totally wrong. These eddies are doing this because that's in their nature. That's their dynamic. It's a Hamiltonian process, not a distributive process. So this is Kolmogorov in 1941 realized that this the cascade is Hamiltonian. And it's Hamiltonian, of course, until the scale of molecular viscosity, which I'm going to compute for you in a few minutes. So, if that's true, then, well, what does that mean? Well, what it means is that we can actually derive the scaling rule. So here's the consequence of this. We're going to imagine that energy is being input here in some rate epsilon. It's being dissipated out here in the same rate epsilon. In between, it's being transferred through these different scales without dissipation. So it comes in one end, comes out the other, and that process then is not governed by viscosity.
Is that a claim or assumption, or what is this?
It's an assumption, it's an insight. Okay, you could say that if all of turbulence research for the last 60 years has been to try to understand in detail this insight.
I mean, if you have laminar flow in a pipe,
This is not true for laminar flow in a pipe.
right, there you have dissipation.
There we have dissipation. I'm going to get to the concept of dissipation in just a minute. So we're just going to go with this insight. So let's ask ourselves, let's now do some dimensional analysis. So what we're going to ask is, what is the formula for epsilon? Well, it's going to depend upon the mean flow velocity, so it's going to depend on the characteristic velocity u. It's going to depend upon the scale, the largest scale in the system, that we'll call L, as the scale at which we're feeding energy in, so it's going to depend upon L. You would think it would depend upon the viscosity of the system, so you would naively have guessed that there would be a nu coming in here. Well, I've just told you that we are going to posit that this process is a Hamiltonian process, so this is out of the dimensional analysis. And that's out of the dimensional analysis, then the only dimensional quantity we can make that has a dimension of epsilon is u cubed over L. Just the same variable that I ended up with when I was working out the speed of the river. Similarly, I could also do the same thing for looking at these structure functions. So let's go ahead and do that.
No. U cube over L is dimensionless?
No, it's not dimensions, it's the dimensions of epsilon. Well, it's the only thing I can make that will go in. Okay, so let me now work out the structure function. So I'm going to compute S of R is the expectation value of U of X of R minus U of X, dotted with R over R raised to the nth power. So let's have a look at what these things have as their dimensions. If I've done this right, the Sn has dimensions of L over T to the nth power. The only variables we're going to use are epsilon, which has dimensions of L squared over T cubed. I have R, which has dimensions of length. And so the only way I can construct a quantity that does not involve viscosity, so no viscosity. So if Sn is only a function of epsilon of R, then it has to go something like this: some dimensionless coefficients times epsilon times R to the n over 3. And so that says that the nth order structure functions have this particular scaling here. And in particular, we can look at what I would get if I chose the second order structure function. So for n equals 2, which is usually the simplest one that one can measure, so that says that S2 of R is going to go as some coefficient called C2 times epsilon of R to the 2/3. And usually what we do is we Fourier transform this. So we Fourier transform and we write it in terms of the energy spectrum, which is the kinetic energy, turbulent energy, wave number range. And so that's defined as 4 pi k squared, the expectation value of the expectation of uk squared, and then just doing a Fourier transform of this, I get epsilon to the 2/3 times k to the minus 5/3. And that's known as the K41 scaling rule. So this simple argument then has a very strange consequence. It says that we have a picture that looks something like this. If I draw the energy spectrum as a function of K, what I'm going to get is something that's completely different from what you might have expected. So here is wave number. So this is large scales, large spatial scales. This is small spatial scales. And up here at large scales, we have scale 2 pi over L, where we're injecting energy into the system. So this correlation function looks something like this. And then what I've shown you is that if you believe this picture, then this goes like a parallel, like this. And then eventually you get down to some small scale where something funny happens. That's where dual heating comes in. And so we get another scale here, which we'll call the Kolmogorov scale, which I'll write as 2 pi over eta k. Eta k is going to be Kolmogorov. So this thing here is called, from here to on here, this is the range of scales that are known as the inertial range.
I feel compelled to inject that it's called the inertial range even if the exponent is not minus 5/3.
Indeed, indeed. It's called the inertial range because in this range here, the flow is driven by inertia. You have this cascade process. If you believe the scaling argument, you would believe that this exponent is k to the minus 5/3. It actually has some small corrections to it, which I'm not going to go into right now. But it's still called the inertial range. We'll talk in a little while about two-dimensional turbulence, and we'll see that something different can happen here. But you still have a cascade process. So that's that's K41. And the other thing you can do is you can take the formula that we have over there for the general structure functions, and you can set n equals 3. So if you set n equals 3, then what you get is that S3 is equal to epsilon r, and in fact, what is actually more accurate statement is that is a precise result from the Howard relation. The Kolmogorov relation says that this is minus 4/5 times epsilon r. So this the scaling argument correctly gives you that the third order structure function is proportional to distance. Okay, and there's a separate law for what happens in two dimensions. So that's the idea of structure functions as they come from this simple scaling. Yes?
So what information about your system are you actually getting from this third order structure function?
Well, the sign is going to tell me about the direction of energy flow. And this is the only exact statement that we can really make about turbulence. So apart from model effect,
So it's something that can be predicted analytically that turns out to be a good, but is somewhat useless beyond that.
it's not completely useless. If you live in France, you will do the following. So what you'll say is this. Let's suppose I want to measure S2 of R. I'm doing some turbulence experiment, I'm trying to measure my correlation functions. The only problem is I don't have a very big budget. So instead of spending millions of dollars and getting Reynolds numbers up to 10 to the 7th or 28, I can't afford to do that. I can only get Reynolds numbers up to 10 to the 5th or something like that. So you say, aha, wait. So this, I can do a trick. So in a minute, I'm going to show you how big is this range here. I'm going to show you that this range is something like Reynolds to the 4 thirds. And then divide that into 2. So how big is the inertial range depends upon the Reynolds number. If you've got lots of money, you need lots of money, because the higher you go up, the more the turbulent drag goes up, and so the higher is your energy budget. Okay? The higher up in Reynolds number you go, the bigger is this range, and you can get 1 decade, 2 decades, 3 decades, and make theorists very happy. But if you don't have a lot of money, you can't do that. But so all you can do is you measure S2 of R, and you plot the data as a function of R, or as a function of K, let's do it in K space. And so you get something that looks kind of like that. And then you're going to try to convince the referee, well there you go, there's 1 5/3, and the referee says, oh, that's no good. So then you say, I can do something clever. Because instead of plotting against K, or equivalently against R, I can use this. So I can now plot S2, not against R, but against S3. S3 is basically R. So now if I do this, plotted against the third order one, I get a nice straight line. Okay? So using S3 as a proxy for R improves scaling. And that's got a name, it's called extended self-similarity. So that's a great idea, and you might say, well, why do I say that only people in France do that? Well, of course, that's not completely true, I'm only saying it as a kind of joke, but the point of it is this. If you do this, well, people say, well, why should this be true? Okay? Why is it better to plot S2 against S3 rather than R? Well, there's actually a serious theoretical reason for this. Not one that I can prove rigorously and mathematically, anybody else can. But nevertheless, a sensible one. And that is that when you have a scaling phenomenon, there's two things that can happen. One is that probability distributions become scaling invariant. Probability distributions that govern the whole functional form of the velocity field in space and time. That scaling invariance then tells you that the moments are functions of each other. However, it doesn't necessarily mean that all the moments themselves have to be parallel functions of the independent coordinates, the spatial coordinates. So you can have data collapse, meaning self-similarity of the probability distributions, before you have data collapse of the actual moments themselves as a function of wavelength. And we know that this can happen because we've seen this for sure when we've looked at scaling laws and phase transition commandments in the 90s. So this idea, this notion, in some circles has a kind of shady reputation in terms of community. But you can understand this in quite a lot of detail looking at phase transition commandments. So I think it's actually a perfectly fair thing to do, and that's why people use it and get quite good results. Now let me just tell you about one other rigorous result, which I think is an important one. And it also is a good point to make a comment about rigorous statements that one can make about turbulence. So the other, I will tell you about some exact results. So another exact result is the Constantine-Doe impact. So this is interesting because this was only discovered about 20 years or so ago, and it was proved by relatively elementary methods. I mean, I don't remember what a Sobolev space is. Does anybody here remember what a Sobolev space is? No, okay. But you know something in math and functional analysis. So even if you don't know what a Sobolev space is, you can still follow this proof. Okay, so it's one of those nice things that is important and deep and actually can be understood by physicists. So the idea is this. It says you take a box with a size L and you make it obey Navier-Stokes. And what you can then prove is that the energy dissipation rate epsilon is bounded by some coefficient times u cubed over L. And u is some characteristic velocity, so you could say 3/2 u squared is the integral from 0 to infinity e to k to k. And so that's the idea. And this is proved just from the Navier-Stokes equations. So what do you expect to see if you were to plot this out? So here is a Reynolds number. Here is epsilon divided by u cubed over L. What you find is that this has the following functional form. It has some variation at low Reynolds numbers, and then indeed, as you go to higher and higher Reynolds numbers, this bound gets saturated. This is exactly the estimate that I used already twice in today's talk, but now this bound can be proved rigorously. Now here's the interesting thing about this. Notice that I didn't say that there was a turbulent fluid in here. I just said there was a Navier-Stokes fluid. And this is one of the big problems. If you try to prove something rigorously about turbulence, you don't really have something like an order cloud. So Diane talked about superfluid turbulence, where you had this order cloud that was made along the Schrödinger equation and things like that. That sort of goes back to these sort of typical condensed matter physics ideas about order parameters or symmetry breaking and phase transitions and so on. But when you're dealing with a differential equation, you don't really have, a way in the mathematics to say, okay, now the equation is turbulent, now it's not. Nobody knows how to do that. That's why, when Konstantin and Döring proved this, this was just a bound. They could just prove that this was limited by the properties of the differential equation itself. Didn't mean that they proved anything about turbulence, didn't mean that it had anything to do with it, because there's no way in the mathematics to represent, say, here's the fluid in its turbulent state, here's the fluid in its laminar state. So, nevertheless, this is a very suggested bound, and of course it's very consistent with the sort of scaling theories that people that have been shown you already. Let me, I think I'm going to answer your question.
It's a comment.
Yeah.
It's just that it's interesting because it shows that fluid dynamics in this emergent state, which is turbulence, comes close to giving you as much dissipation as you could possibly have, given the governing equations motion.
Yes, exactly. That's very, very good comment. And,
What if the other equation you wrote down on the spectrum? That integral?
this one here?
The u squared.
I just defined for you how you might define what u is.
What u is.
Now, so let's just see how surprising this result is. So let's ask ourselves, question, if I hadn't told you this result, what would you have guessed? So what you'd say to yourself is, well, think, we know that the Laplace equations is du by dt is equal to some stuff, and then there's this term nu del squared u, so you would have guessed that the epsilon is something like d by dt or half u squared, so then you would have said, well, therefore it should scale as something like nu u squared over L squared. That's what you would have guessed. But the Konstantin-Döring bound says something different. It says that the epsilon is going as u cubed over L. So if you now look at what is the ratio between, let's say, epsilon simple, epsilon Konstantin-Döring, then what you would have got is the following. The ratio of epsilon Konstantin-Döring to epsilon simple is then u cubed over L times L squared over nu u squared, and that is ul over nu, and that is equal to the Reynolds number, which we will assume is what's being. So this bound is a bound that's likely to become more and more appropriate as we go into the Okay, so now I've told you a little bit about similarity and scaling. So now I want to tell you some more scaling laws. So I want to answer the question of how wide is the inertial range as a function of energy. So we've talked about the energy input, we've talked about the energy cascade, but we haven't talked about where the energy actually goes. And that's what I'd like to do for you now. The next question is, how does the size of the inertial range scale with Reynolds number? So what we're going to do to answer that is we're going to go back to this very simple argument that I gave you at the beginning when we tried to work out how fast a river flows. We're going to look at this idea of eddies, and we're going to try to construct time scales, and from those we're going to try to work out at what scale the flow gets so slow that we start getting into the range of viscous dissipation. So the basic the idea is a look at the kinematics of edges in the inertial range. So when I talk about R, as I'm going to do right now, what I'm talking about is a scale R, which is in the inertial range, not range length states. So I'm going to have an eddy turnover time. How do I get that? Well, I get that eddy turnover time by getting the scale R and dividing by the velocity on that scale. So that velocity on that scale, UR, I'm going to get from the previous estimates that I made before. So UR is going to go something like epsilon R to the 1/3. That's an estimate of the time it takes, or this is an estimate of the time it takes for energy to be transferred from one scale down to the next scale. So then I can define a scale-dependent Reynolds number. So Reynolds is a function of R, which is going to be UR times R over U. Okay? So this, by the way, I didn't say it clearly. This thing here just comes from our Kolmogorov scaling. So if S2, which goes as U squared, is going like epsilon R to the 2/3, then I'm going to estimate that the velocity goes like epsilon R to the 1/3, just by square root. So now I have a Reynolds number that depends on the scale like that. And so that basically goes then as epsilon R to the 1/3 times R over U. Now I can ask, well, what happens if I go to one end of the inertial range up to the scale where I'm forcing the system? So let's now look at two cases. The first case is we're going to set R equals L, and that then says that the Reynolds number on the largest scale of the system, which is usually the scale that experimentalists will quote in order to impress you with how turbulent their experiment is. So you choose the biggest scale you have in your system, and then you quote a Reynolds number based on that scale, and it's always going to be big. Okay? So this number then is epsilon to the 1/3, L to the 4/3 over nu. Then the next case is we're going to choose, so that's case 1. Case 2, we're going to choose R equals the scale I call the Kolmogorov scale, I call it E to K, and this is going to be the scale such that epsilon is going to be going as nu squared over L squared. So in other words, we have viscous dissipation. So, in other words, what that says is that the Reynolds number is going to be some number of order unity. It's going to be 1, or 5, or 10, or 100, or something like that. It's not going to be tending towards infinity. So then, I can say then that means that I'm going to define the length scale E to K by the requirement that Reynolds at that scale is equal to 1, or at least order 1. And so that tells you then that 1 is equal to epsilon to the 1/3, E to K to the 4/3 over nu. And so that means then that E to K, Kolmogorov scale, scales as nu times epsilon to the minus 1/3 to the power of 3 cases. So what that means is that now I can look at the ratio of those two scales. So if I look at the Reynolds number as the ratio of Reynolds over L over Reynolds over E to K, and that is going to be L over the Kolmogorov scale raised to the power 4/3. And so what that tells you then is that L over E to K is Reynolds to the 3/4, and if I want to ask how many degrees of freedom are active in turbulence, and so I've got the ratio of L over eta. That tells me how many scales in one dimension. Typically I'm in 3 dimensions, so what I have to do is say that's going to be L over eta k cubed, and that's going to go as Reynolds to the 9/4. So that means that if you try to simulate turbulence on a computer, you're doomed to failure, because however big your computer is, I can crank up a Reynolds number such that it breaks the computer. Like the number of degrees of freedom, going as Reynolds to the 9/4, will break your computer. That's the form that, again, Dan showed you in his talk.
It keeps the experimentalists employed, though, so that's.
So again,
It keeps the experimentalists employed.
I think keep the experimentals important. Alright, so now I want to just finish this part about the scaling laws by telling you about the limitations of them, and I want to end by telling you about 2 dimensions. So far I've told you the sort of gold standard K41P, and it's known to be, I mean, it obviously contains elements of the truth, and there's experimental data that you either see or in future or down to afterwards, showing you agreement with measurements made of the tidal estuaries, of K, showing you the application of those 5/3. I'll even show you some data on this in my talk tomorrow. But I want to tell you about deviations from K41. So why are there deviations from K41? Well, there's deviations because we've made a very strong assumption. The first question is why? Why are there deviations? And there's actually 2 kinds of answers. So one answer is we assumed that you can neglect the viscosity. Now, what did I tell you on lecture 1? Small is not negligible. So the fact that we can assume that viscosity is unimportant because we have this great insight about the cascade and so on and so forth, doesn't mean that we can neglect new interdimensional analysis, just like we were seeing all of last week when we were looking at the low Reynolds number flow. So we assume that we can neglect new, but maybe there is intermediate asymptotics of the second kind. And so the structure functions have to be modified by ratios of the small scales to the large scales, and we can have a scale interference. And so that says that S2 could, in principle, have other terms involved in it. Could be over R, could be eta k over R, and so on. So there could be corrections to that, dimensionally allowed corrections. That could be small, but could have very strange singular forms. And indeed, there are known to be things like this. So, for example, it is known that there exist intermittency corrections. Really, turbulence is not a pure Gaussian field. Things come in bursts. Ask anybody who's ever been in an airplane. So what these intermittency corrections give you is that E of k goes like k to the minus 5/3, but there can be some anomalous experimenting.
There is, right?
Well, there is. Well, I'm saying in principle there can be, and in practice there is. And eta is an anomalous experiment, or the intermittency experiment, and it's very small. It's about 0.02 or something like that. Hard to measure exactly. I'll talk a bit more about that tomorrow. So you can have corrections here, and of course, as you know from last time, because I've got corrections there, there's also corrections that come in here in order to make sure that dimensional analysis is fully satisfied. So that's the first type of correction that you will get to K41 scaling. Another kind is actually potentially deeper and more interesting. That's type 1. Second kind is the second type is higher order numbers. So, if you want to measure the second order structure function, you measure velocity correlation function. That's not trivial, but it's doable. You can, if you're lucky, measure the third order structure function. If you're really ingenious and you can do really high precision experiments, you can measure structure functions S3, S4, S5, S6, S7. I think people can measure S8 and so on. You can measure very high order things. And so what you would expect, based on K41, by the way, K41, Kolmogorov himself never said this. He never made this claim, but people often attribute it to him. And so Sn of R should go as epsilon R to the zeta n, and zeta n is it over 3. That's what you would expect based on the K41 scale. In fact, if we go and measure those exponents, and often those measurements involve using that trick I told you about, that extended self-similarity trick that people in Europe like to do, then you can obtain estimates for these exponents that are quite different from the K41 ones. Let me just give you an example of some of those.
So these experimental results?
Yeah, so experiment. So zeta 3 is 1.0, zeta 2 is 1.70, zeta 4 is 1.28, zeta 5 is 1.53, zeta 6 is 1.77, and so on. And if you look at the naive scaling, what you would get is, which is in different color, so you get 1.0, you get 0.67, you would get 1.33, 1.67, 2.0, and so on. So there are definite departures. This exponent depends in a non-trivial way on n. In other words, whatever moment you're looking at, there's a different exponent. It's not just to get the nth order, you just take the first order and multiply it to the power n. So there's a functional dependence there, and so that functional dependence is what's known as multifractal scaling. So this was a big field of activity during the 1980s and 1990s. Okay, so what I want to do now, I've got about 10 minutes or so. So in my notes I discussed for you about wall-bounded turbulent shear flows, so I'm going to skip that. I want to talk to you instead about turbulence in two dimensions.
Probably worth commenting that there's nothing strange about that. In a sense, like any non-trivial field theory, away from mean field regime. Would you agree, Margaret?
Say, what was the question?
Well, I'm just commenting that there's nothing there's nothing odd about this. Any theory that's non-trivial, any system that's non-mean field-like, away from Dr. Richardson, will have this kind of non-trivial response for every moment.
So the people, I wouldn't agree with that. No. So most field theories at the critical point are showing fractal scaling, and not showing multifractal scaling.
If you compute correlational in the Ising model.
You can compute correlations, but there's still only one scale that's set in the scale range. So there are few theories that will do this. And in fact, if you have, for example, if you have asymptotic freedom in certain gauge theories, you can get this kind of multifractal scale. It's not the same thing as what we usually used to in critical field.
So do you take an Ising model at critical points,
No.
dimensions, it's compute phi to the n?
You still have only one. You still have a scale invariant probability distribution, but here you don't have a scale invariant probability distribution. I can't write the functional probability distribution as one single function. I'll discuss with you afterwards. Okay. You only took half my remaining time. So can I have that for next minutes?
Sure.
Good. Okay. So the last topic I'm going to talk about briefly is the turbulence and turbulence. So what I want to show you is that this picture kind of applies, but not quite in 2 dimensions. So I'm going to show you, first of all, that there is no vortex stretching in 2 dimensions, because the singularities are more point-like than line-like, and that you can get dual cascades. And there are conserved quantities beyond energy, and those quantities can also cascade, and that gives rise to experimentally observable results. So let's start off with the vorticity equation. So the basic idea that we're going to be thinking about is that we're in 2 dimensions. And what's special about 2 dimensions? You all know this. You all know that in 3 dimensions, rotations don't commute. And in 2 dimensions, rotations commute. That means that any vorticity variable is going to, if you have a turbulence in the plane, the vorticity is going to be pointing perpendicular to the plane. And so the vorticity rotations will just be in that plane, and so they're going to commute. Things that commute are conserved quantities. And so you're going to see that there's a conserved quantity, in fact there's an infinite of conserved quantities, that relate to the commutability of the rotational operators in 2 dimensions. So let's have a look at the Navier-Stokes equations. So Navier-Stokes, we write down du by dt, so by this operator, body derivative, I mean d by dt of u plus u dot grad u. And that's minus 1 over rho grad p plus nu del squared u. Okay? Now we define the vorticity, omega as curl u, and then we ask, well, what is the equation of motion for the vorticity? So you can work it out, and what you get is if I look at the components of the vorticity, so vorticity is a vector, so if I look at d omega I by dt, that's going to look like omega of grad ui plus nu del squared omega I. So that's the vorticity equation. Now let's suppose that at some point in time, t, omega happens to look like this. Omega 0, 0 in the xy plane, and then just has some component in the z direction. So then what the vorticity equation says is that d omega z by dt is basically going to be proportional to omega z duz by dz plus terms that scale with mu. I'm not going to be concerned about those at the moment. So what that says is that the vorticity is increased by gradients in the velocity field. So I have velocity gradients, they tend to increase the vorticity. So if du by dz is greater than 0, then it's going to increase omega z. And so what that tells us then is that in 3 dimensions, vorticity is not conserved. So for example, if I have a funnel The fluid is flowing through it like this, in some turbulent way, flowing down under gravity. What happens is that the fluid accumulates omega z, and it increases in the direction of increasing velocity gradient. And it does that because the fluid, as it goes around here, the angular momentum is causing it to swing faster and faster and faster. It's increasing the velocity gradient and stretching out the vorticity. So vortex lines, if you start off with a fluid, you start off with some vortex line, it gets immediately transported by the flow, and it becomes something much more complicated later on, in 3 dimensions. Now, in 2 dimensions, something special happens, and one of the first people to really draw attention to this and make it clear that this had some really real important effect in turbulence was T.D. Lee in 1952. So in 2 dimensions, you can have omega is just 0, 0, omega z, but the velocity field is ux, uy, u0 in 2 dimensions. And so what that means is that the term in the vorticity equation, omega dot grad u, is always going to be 0. And so that what that says is that d omega and dt is small, something that just is 0, plus terms that go like u. So what it says is that in 2D, vorticity conserved up to molecular viscosity. Okay, so I want to end by giving you some homework assignments. So what you can do now is, using these ideas, you can now go and work out the analog of K41 for 2 dimensions. So let me just close by writing up a couple of quick assignments on the blackboard. I'm not going to have time to go into all that can be said about 2 dimensions, but I'll talk a bit more about that in tomorrow's lecture as well. So here's exercise 1. So exercise 1, let's assume that nu is equal to 0. Then calculate the quantity z, which is 1 over area, integral over area, omega squared d2r, and show that it is a constant of motion. And in fact, all moments of omega are conserved. So in fact, there's not just this one, but an infinite number of others. So that's part A, part B, show all other moments conserved as well. This one here is of particular interest because it can be easily measured. It has a name, and it's called the Emergent. Okay. So let's homework exercise number 1. Homework exercise number 2. Show that E is 1 over area integral u squared d to r is conserved. And u equals 0. Okay, so that shows you that there are 2 conserved quantities, or at least 2 conserved quantities in a cascade in 2-dimensional turbulence. Okay, now this last exercise I'm going to give you, there's some others here, I'm not going to give you all of them, but the last one is a really good one. So, let's find it. Exercise 3. assume that there is a rate of entropy cascade as well as a rate of energy cascade. So assume beta is dz by dt, just like epsilon is minus dE by dt. So we're going to assume there's a cascade of entropy in 2 dimensions, and there's going to be a constant rate of entropy cascades, which we'll call beta. Then I want you to go and work out, use dimensional analysis to prove the following things. That 1 is the analog of the Kolmogorov scale. Scales like nu to 1/2, beta to the minus 1/6. And then, number 2, that the energy spectrum associated with entropy is E of k entropy cascade, is E of k goes as k to the minus 3. So you can have a cascade in entropy as well as a cascade in energy. Okay, so those are the exercises. There's a couple of others. I want to show you one last fact, and then I'm going to be quiet and then do one. So one last thing I want to show you is what the energy spectrum looks like in real energy, in real 2-dimensional fields. There's one more surprise here, and if you look through the notes, I explain how this can happen. So the last surprise so here's K, we're going to be in 2 dimensions, with the energy spectrum. I'm going to inject energy into the system here. So this is the injection state. The injection scale to minus 1. So what's going to happen is this. You're going to get a cascade that goes as k to the minus 3 due to entropy. But you can also get a cascade due to energy, and that has to go as k to the minus 5/3 by dimensional units. Here's the thing that's strange. The entropy cascade goes down to small scales, up to the scale that we talked about there, into something like that. And so this is indeed k to the minus 3. Then there's a scale where, then you get a range of scales where you get k to the minus 5/3. That's the energy cascade. You can ask yourself the question, which way does energy flow? And you can work that out, and I'm not going to go through it for you. I'm just going to tell you the answer. The entropy cascade goes to smaller scales. The energy cascade in 2 dimensions is an inverse cascade. So you have 2 coexisting cascades. This inverse energy cascade, this was first suggested by Batchelor in 1953, page 186 of his textbook, and then by Richardson, worked out in great detail by Richardson and later many others in the 1960s, and so you have this 2 others. So one last puzzle. One great example of 2-dimensional turbulence is the atmosphere. The atmosphere is a thin layer around our perfectly spherical cowl planet. It's a fan experience. So you would say, well, it's 2-dimensional, so therefore we should have a picture like this. What we should see is that at large scales, small k, we should see k to the minus 5/3. At small scales, we should see this. And you do see these cascades. You can see them. There's wonderful, beautiful data that shows you the atmospheric spectrum with these 2 things. The only problem is that these cascades in the atmosphere are the opposite way around. And how can that be? Actually, it's a compression. Nobody knows. So tomorrow, I'm finished, and tomorrow I'm going to tell you, I'll maybe make a few more remarks about things I think that we might forgot about today, and then what I'm going to do, is I'm going to explain to you some new work that we've been doing, which is trying to connect the strongly fluctuating and turbulent fluid picture to a picture of statistical mechanics and critical phenomena, and I'm going to show you how that happens. So that's all for today. Thank you.
We've already eaten into 10 minutes of lunch, so perhaps questions can be had while
Well,
walking.
it turns out there's plenty of free time for lunch in the Because we've all been here last week, so
But some people might be hungry.
That's right.
So let's go ahead and break for lunch, and I'll be back here then at 2:30.